Yes, my name is Meewis, and we did this study that shows that Guinea baboons have a preference for agents in chasing interactions. So what we wanted to do in this study was actually to compare how events were processed in non-human animals compared to what we know from humans. And from human adults, it is clear that we are constantly bombarded with an enormous amount of information. And what we do with this information is that we are able to detect separate events and furthermore extract event elements that are relevant. And we are also sensitive to the relationship between them. And we can describe how we cognitively treat this with this phrase, who is doing what to whom. So here we have the who denotes the agent of the action. This one is performing the action and causing a change in the patient, the whom, which is the undergoer of the action. And what is interesting is that when we describe events, actually these same event elements are popping up in the linguistic structure. So the agent is described by the subject of a phrase and the patient by the object. Now, this parallel has actually influenced some theories that say that perhaps the structure of language has its roots in the event cognition, and it could be the case that the event cognition is actually evolutionary old and shared with other species, and it is just in the human lineage that it has become externalized also in the way we talk about events. And as I said, agent and patient are very prominent event elements. And what we know is that agents have a specific status. They are preferred in how we perceive events. So when humans observe scenes, they often look first towards the doer and also often for a longer time towards this agent. And again, we see this paralleled in linguistic descriptions because most of the languages emphasize the agent by setting the subject first in the sentence. And this we can see really across the world in different languages that the subject-object-word order is most prevalent. And this has prompted the agency detection hypothesis, which states that possibly the fact that we have this cognitive bias to look at agents, that this has also popped up in our linguistic descriptions, and it may be actually the root of this structure that we see popping up in different languages across the world. So it also assumes that this cognitive treatment of events has probably evolved for non-linguistic reasons, and therefore it could also be shared with other species. Now we took chasing as our case study, because chasing is a simple event which shows an interaction between an agent and a patient. We have the chaser, who is doing the action, so it's the agent, and the chasee, whose behavior is caused by the patient. Who is caused by the agent and is therefore the patient. And as has been discussed previously also in Sandra Waxman's talk, is that when we use actually simple geometric shapes, also the motion patterns alone can give the impression of sophisticated behaviors, such as chasing. And what we know is that it's very easy for humans, children, and infants to discriminate chasing from other two-actor displays. And the same is true for some non-human animals who are able to discriminate and tell apart chasing from other two-shape movements. But more importantly, also for chasing, it has been shown that there's this agent preference. So there's an increased attention for the agent, which is in this case the chaser, both in human adults as well as human infants. But we don't know really how this works in non-human animals. So this is what we tested in this study. We wanted to know if Guinea baboons would also show this attentional preference for the agent in a chasing interaction. And we tested this with a change detection paradigm. So what we know is that people are faster to detect changes in areas where the attention is already directed. And similar types of studies have been shown to work as well with non-human primates. So what we did is we actually showed a chasing display to the participants. So we have two shapes that are moving across the screen, and after a while, one of them would change color. And the task for the participants was just to detect this color change and then tap it. And if they did so correctly, we would reward them. So we hypothesized that Guinea baboons would also have an agent preference, so we expected that their attention would be attracted by the chaser, making them also faster to detect the change. And we pre-registered this hypothesis as well. So how did we do this with the baboons? So our setup looks like this. There's a group of 23 baboons living in a facility in the south of France. And here they have free access to testing booths where we have touch screens where they can participate in the experiments. So here they can go in and out whenever they want, and we can show the experiments on the screen. And we use an operant conditioning style, meaning that they are rewarded for good responses. Now we had the chasing stimuli, and here there's always two objects, the chaser, who is the agent, and the chasee, who is the patient, and it looks like this. So there's two objects, and then one of them changes color. So we programmed it this way that always the characteristics of the chaser was to go towards the chasee, and the chasee would then flee away when the chaser was close. And we made a very subtle color change so that the participants really had to pay attention to where this color change would appear. And of course, it was applied both to the chaser and the chasee. And I don't know if you could just see the color change, but I'll point it out to you. So we have here that the color change happens. Right, it's very subtle. Now, we also wanted to make sure that any preferences were not just explained by a preference for the motion patterns, because obviously they have different velocity styles which are programmed by us. So we created this random condition where we again have two objects, but they are not moving in accordance with each other. So the first object moves as if it is being chased away, so it's fleeing. And the second object moves as if it is chasing, but they are just not moving synchronized to each other, which looks like this. But it's important to note that the motion patterns are exactly the same as in the chasing condition. Another option for potential preferences could be due to the fact that they prefer the first or the second object because they move in order. So for this, we created a following condition. And interestingly, here we have two objects that move in a synchronized way. But now we have the first object, who is the agent, who is leading the path, and the second object, the follower, who is the patient, because its behavior can be explained by the behavior of the leader, and that looks like this. So they come together, the first one moves and the second one just follows. So we have these three different displays. Chasing and random have the same motion patterns, but they are not synchronous in the random condition. And chasing and following both have a first and a second object, but the agent and patient roles are not the same. Right, so let's go to the results. And I can show the results of 13 baboons who participated. And I will show you the reaction time. So that is in milliseconds, the reaction time to the color change. Let's start with the chasing. So here on the left, you can see the first object, which is the chasee, the patient, and on the right, the second object, who is the chaser, the agent. And you can see that the direction of the effect is towards faster for the agent. But it's important now to compare this, of course, to the random condition. And here we found a statistically significant interaction effect with the random, meaning that we cannot explain the finding in chasing just because of a specific preference for the velocity pattern. And if we look at following, we can find an effect which is kind of in the middle of the other two. But it was also significantly different from chasing, meaning that also the effect cannot be explained by a preference just for the second object. So we asked in this study whether Guinea baboons would also have an attentional preference for the agent in a simple chasing interaction. We found an effect that was in line with this idea, and it was different from the other two control conditions that we had, random and following. So the reaction times that we found for chasing cannot be explained just by a simple preference for one of the motions of the chaser or the chasee, and not because they just preferred the second object. So this really points to an attentional preference for the agentive role in this interaction. And such an attentional preference is comparable to what we know in human adults and also in human infants as young as 5 months. However, we did not find the opposite effect for following. I was expecting that possibly because we switched the roles, they would also show this agent preference for the leader in the following interaction. We think that perhaps this one was less salient as we based it off the chasing animations. And the two objects, they move much more similarly compared to chasing. However, we also know that it works the same in human infants that show a clear agent preference in chasing, but not so much for following. So we are left with the question whether we can extrapolate these findings beyond chasing. Now, this attentional preference that we found for agents in Guinea baboons appears to show that an agent preference could be part of an evolutionary old way to process events, and it also points to similar event processing in non-human animals, non-human primates in this case, and human primates. It's also in accordance with the agency detection hypothesis, so we can speculate whether the subject-object word order prevalence has its evolutionary roots, possibly in a shared event cognition. And with this, I would like to thank my thesis supervisors, Isabelle Dautriche and Nicolas Claidière, and also my collaborator, Joël, Fagot, and the people at the primatology station who helped out, and you for your attention. Thank you.
Thank you very much. So we have some time for questions.
Thank you. This is very nice, and actually, you are right. You are replicating something which is known in adults and children and infants, human infants, so they pay more attention to the chaser. I just want to warn you that it's not quite clear how this is actually dependent on agency, in the sense that you said that it is the chaser who is. This is an interpretation. The chaser who is causing the chasee to flee. But in terms of dependency in motion, it's actually the chaser's motion depends on the chasee's motion in this case, and it is well predicted by the chasee's motion and not the other way around. So it's possible that it's, the effect is at least partly depends on predictability. It's easier to follow the chaser than the chasee, which is randomly changing directions and speed and so on. So that's one possibility. It's interesting that you didn't find this in in the following case. But in the following case, they are closer to each other and they are moving to each other. So they are both of them are equally easy to follow.
Mm-hmm. Okay, so thanks for your question. So what I think is happening with the chasing is how it starts out is that the chasee is moving around randomly and then the chaser goes towards it. So the very first movement is by the chaser. And then I think you're right that it's kind of a cycle effect. So the chaser moves towards the chasee, it flees away, and then it goes on like this. So I think the agentive role is mostly because it starts off with the chaser, and this one is who initiates the cycle. Then for your second question, which was about the I think it's the comparison with the random that is very important here. So we cannot just say that it's because of specific motion, because we see actually in the random that they appear to find it easier to click on the chasee, possibly because it has a more erratic type of movement. But this completely reverses when they come together in synchrony. So this is why we think it's really because of the agent role. And lastly, you said about the following. Can you maybe repeat this?
My comment was that in the following case, they are equally easy to track, both of them, simply, and therefore easy to
Yes, I think you're right. Yeah. They're just less easy to tell apart, let's say. Yeah, I think this could explain why it's kind of similar how fast they are in their response. I can also add that for accuracy, they were approximately the same across conditions.
More questions?
Thank you very much for the talk, very interesting. I probably missed a point, but because the animals are freely going to the boxes and there is no actually control on that, how many times the same animal was exposed to a particular condition? Did you control for that? And in the same line of questions, actually, how do you control, given this freedom that the animals have, which is nice because somehow it's a control for the motivation for playing in the game, but how do you control that they are equally proficient in responding? Do you have a kind of tracking of the number of times they went? Did you control that? How do you balance all these conditions?
Yes, thanks for the question. So how it works is we wanted to obtain 800 trials per condition, so 400 for the chaser and 400 for the chasee, let's say. So yes, we keep track of how often they go in and at which point they leave off in the experiment. So let's say they have done 10 trials, the next time they go in, the computer recognizes who it is and it continues with trial 11. So yeah, that's how it works. And yes, there is a training phase that is happening before the experiment takes place, and this was just to familiarize them to what is a change detection task. Here we always had just one object that was moving and it would change color. And we would incrementally also increase the time they had to wait before this color change appeared, because we really wanted them to see the actual animation play out before one of the color changes would happen. So yeah, there was training before this. Thanks.
Just a very quick question.
Thank you. I feel so lucky to get to ask it. I don't know much about the visual perceptual capacities of your participants. I do understand, and thank you for a great talk. I do understand why you would use the minimalist agent and patient Here, it's a lovely way to tease apart the abstract roles, to try to tease apart those abstract roles. But I wonder, what would you predict, or why is it a really dumb idea to show these baboons conspecifics in precisely those circumstances? That is, I would imagine you could get some control over temporal characteristics and paths. And if not, I bet you could use humans, which would be closer to true agents than the dots.
Yes, thanks. That would be actually super interesting, I think. So while it is very interesting, it's also much harder to implement. So imagine creating, let's say, chasing videos of some kind of two monkeys. You would also, of course, want to control for the size. Maybe they know the individuals, who is dominant, who is not. So, yeah, I think we are thinking going towards this, but yeah, just how to implement it is definitely tricky. So I think. Yeah, why not? Yeah, I think that could be the case. It's just that here it's just interesting to know that just the motion cues by itself are already enough to elicit this effect. So thanks.
Thank you very much, Flor.